Alrighty, let's pretend that I've got a parabola, y is equal to x squared, and we're going to look at a section of this thing. So let's look at the vertical line going through x equals 2, and then we'll also trap it with the horizontal line y is equal to 0. So if I look at this region of the graph, let's pretend that I want to spin this thing or rotate or revolve this thing around the y-axis and create a solid three-dimensional region. So I would create some shape that looks like this. And you'll notice that this is obviously different than what we've been looking at because we're spinning now horizontally around the y-axis instead of the x-axis. So when I think about taking a cross-section of this shape, suddenly I'm not taking a vertical cross-section. You might agree that if I took a vertical cross-section, there would be not much of a rhyme or reason. But if I take a horizontal cross-section, I've got myself a washer. I've got myself a washer, and I know how to deal with washers, so this is good. So that's what we're going to do. We're going to be looking at horizontal cross-sections. We're going to think about finding this volume by taking an infinite number of infinitely thin slices, and this time stacking them vertically instead of stacking them against each other horizontally. So what this means, if I look at my integral, if I try to set this thing up with the area of a cross-section, the area of a cross-section is now going to be some thickness that is infinitely thin in the y direction. So we're going to be dealing in terms of y. We're going to be looking at dy's instead of dx's, and our area of each cross-section will also be defined in terms of y. So for a horizontal revolution, this becomes my sort of like my model. I'm going to take the area of a cross-section defined in terms of y and integrate with respect to y. This also means that my limits of integration from a to b are now going to be values also of y. So let's go ahead and try to set this thing up. If I look at this shape in the y direction, I am my limits of integration are going to go from 0 to 4. And I've got washers, right? So I'm going to have pi times some big R squared minus some little r squared with respect to y. So I got to figure out what's the big radius and what's the little radius. Let's go ahead and start with big R, and notice that big R is going to be the distance from the axis of rotation, which now is my y-axis, all the way out to the farthest part of the figure, which is going to be a constant distance because of this vertical line. It's going to be a constant distance of 2. And then the little r is going to be a little interesting. The little r is going to be the distance, again, from the vertical line that is my axis of rotation over to the function. So it's going to be that distance, and that distance, and that distance. That's the little r. So this is a little r. That's what I'm trying to eliminate. So I've got to figure out how do I communicate that distance. And really we need to think about what this is. I'm asking what is the x, like what is a function in terms of the x direction? When I talk about the height, when we've done these before, I've been talking about the y value, the output value, which we've called x squared. We've said that y is the same as x squared, and so we're going to use x squared. But now I've got to switch things up. I need to know what is x. What is x? I don't know what x is, but I know what x squared is, and so I can solve for x by taking the square root of both sides. So I can say that x equals the square root of y. This is the same function as y equals x squared, but what I'm finding here is the x distance at any point along this function. So the square root of y is that, and that, and that, and that, and that, and that, and that. So little r is my function solved for x in terms of y. Oh, sorry. That's wrong. What did we say? We said that big R was 2. I don't know how that got erased. Big R is 2, and little r is the square root of y. So when I set this thing up, I've got pi times the integral from 0 to 2 of big R squared minus little r squared. And don't be freaked out by the y's and the dy's. We're going to treat this the exact same way as with x's, only we're dealing with y's, so no big deal. We're going to integrate this just like normal, and let's see what happens. So we can simplify this thing to 4 minus regular old y dy, and anti-differentiate this thing to 4y minus 1/2. Uh-oh. What's going on here? 1/2 y squared between 0 and 2. And we would solve this just like all of our other problems. The bell's about to ring, so I'm going to leave you off here. And we'll pick up with this tomorrow.